Good afternoon. Well, good evening, actually. So I'd like to first acknowledge Katie Karenan and Jeff Abers, Cornell University, and USGS Power Center for Analysis and Synthesis, and then the working group for injection-induced seismicity. And the topic that I'm going to talk about today is looking at the connecting wastewater injection and seismicity through pool pressures. And then my co-authors, Matthew Weingarten, Mark Persson, and Barbara Bekins. And I'm going to say a few words about the nice paper, a nice part of the paper that Mark just mentioned, but I'm going to avoid the dead Nimoha fault. Okay, so this is a map that based on US EPA's database that in US in 2011, there are about 170,000 Class 2 injection wells throughout the 33 states in US. And these black dots shows the indicate the number of wells in these different states from a few tens to more than 5,000. And then superimposed on this map are the red stars are some of the earthquakes that have been associated with these injection activities. And those earthquakes are greater than 3. And the association between these two activities are primarily based on the correlation, temporal correlation, and spatial correlation. And this is example from Colorado, the temporal correlation between the injection volumes and occurrence of seismicity. And then so on the horizontal axis is the time, and then the red bar shows the blue bar shows the injection volumes, and then the red bars show the seismicity. And so the pattern and trend are pretty convincing. And that's a temporal correlation. And then the spatial correlation is quite a bit messier. We don't have a very good clear picture at this point. But I'm going to just bring your attention to a talk by Matthew Weingarten Friday afternoon, 2:55 p.m. Friday. And then if you're still around, go check it out. It's really latest work on spatial correlation. Here I'm just going to show you a very small piece of that work that Matthew will be presenting on Friday. And so this is a map shows the Colorado, and the blue dots here are the injection wells, so all the injection wells, and then the yellow dots are a subset of all the injection wells in Colorado that have been associated with the seismicity. And that's just based on the radius of, we draw a 15 kilometers radius around the seismicity, and if that well is active within a 15 kilometers radius of the active earthquake, and then we call that associate well. And so, and then on the right side, and these are the seismicity map, and then the black dots are all the seismicity from 1973 to early 2014. And then the red dots are a subset of the seismicity here that are associated with the injection wells. And so these are preliminary first cut of the spatial association. As I mentioned, that the broader picture is quite challenging because at this point, U.S. nationwide does not have a uniform standard of the database, so it was quite a lot of work. And so coming back to this map here, and there are many injection wells, only a few, just from this map, are troublemakers. And then we could always ask that question, why is that? And we can look at what are the important factors that contribute to potentially induced seismicity. And so there are several we have heard today that background stress, for example, Mark just mentioned, and stress orientation, stress magnitude, how critically stressed the crusts are, and particularly these injection locations. So it's a definitely very important factor. And then other operational parameters, such as the injection rate or accumulative injection volume and injection pressure, we just said it's irrelevant. Well, for more discussion about that. And then the other geological factors, such as the fault, and I think, again, we heard from Mark that that is critical. And then the injection depths, whether it's the basal aquifer or in the middle level. And so all these are important factors. But what I'm going to focus on today and the next few slides is looking at how pore pressure generated from injection wells that connect to potentially induced seismicity. The basic physics we all know for more than 50 years now, and the two key points are that fluid pressure weakens the rock and then fault slip. And that's a classic paper in the 1950s, and then there are many other papers afterward. And then the further work is that we assume that the crust is critically stressed. And so these are basic fundamentals that, again, we know. And if we translate that in a quantitative way that use the Coulomb stress change to looking at the fault, whether the fault is going to slip. And then you can look at the Coulomb stress change and look at the balance between the shear stress and shear resistance. And I wanted to particularly highlight here, if we look at all these variables, the stress and background and the fault angle and other things, pore pressure is the variable that does change with time. And I think that's what I wanted to highlight here. And in the following, I'm going to just present 3 existing cases that looking at the pore pressure propagation from injection well to potential seismicity site. And so this is a site you have heard from Austin and Mark and previous speakers. That's in Oklahoma. And this seismicity, I think I can go through that quickly. So now this is a nice part that about that paper. And so we developed a hydrogeological model, very simple one. And because there are other complications, and we all learned that the geology is quite complex, and there are a lot of factors we still don't know. So at this point, we constructed, or Matthew Weingarten developed this hydrogeological model. So it's pretty straightforward here. And this gray block here is the basement. And then this is the injection interval on top of the basement. And then here is the Nemaha fault. And then we're assuming it's no flow. And if we call that dead, that's OK. And the dimension of the model is about 130 kilometers this north, east-west, and then 200 north-south, and then 6 kilometers into the vertical direction. And then we took the hydrological parameters from the literature and compiled from as much literature we can, as much as we can get our hands on. And we used a diffusivity of 1 meter squared per second for the injection formation. And then for the basement, we assumed that the diffusivity decreases with depth. And it's higher in the top and then decrease to pretty small by the time you get to the 6 kilometers. And so these diffusivity values that use reasonably produce the pressure values at the overall pressure picture. And so this is the result of the pore pressure modeling. And here is the these two are the plan view. Here's the Nemaha fault. We assume that the other side of the Nemaha fault is not participating in the hydrologic diffusion process. So here the 4 injection wells that at a higher rate. And then this is the 2009, and then 3 years later, and this colored shows the pore pressure magnitude. And so the red region here is about 1 megapascal, and then progressively towards northeast. And these triangles are other injection wells in that area that are at much smaller rates. And so the red dots are the seismicity locations. And so the one thing that I want to highlight here is that the lateral propagation of pore pressure can go to considerable distance of 20 or 30 kilometers laterally. And then in the vertical direction, the pore pressure propagation can also go down to considerable depths. And this color scale is the same as the previous plan view. And this is the seismicity histogram distribution as function of depth. And here's the basement. And so what we can see here that the pore pressure increases, modeled pore pressure increase, and the earthquakes occur, depths are pretty consistent. And that established some confidence about the pore pressure model. Okay, so, and then the other thing we looked at in the model is that as I mentioned, there are some other wells in the northeast area of the domain. And so this plot shows the contribution of these different injection wells. And so the red line shows the contribution of the contribution of pressure from 4 high-rate injection wells. And then the yellow line shows the pore pressure contribution from the rest of the group of wells in the northeast. And then the blue line is a summation of both. So what this primarily shows that the high-rate injection wells contribute a significant portion of pore pressure change. And it's about 85% of the total. And then the other thing we also looked at is to check the pore pressure at these seismicity locations. What are the pore pressure at the time of the earthquake? And this is a histogram of showing on the horizontal axis shows the pore pressure at the time of the earthquake, and then this shows the number of earthquakes that at this pressure. And so what we find out here is that at 0.07 megapascal, and there's a large population of earthquakes happened. Now, this is at this particular site for these particular simulations, and we could suggest that this pressure could be a threshold for seismicity. But is this sufficient to trigger earthquakes in general? And I think that is a more broader question for further discussion. And for example, fault orientations and whether the stress is critically stressed, whether the area is critically stressed, and that those are critical. And so I think, I mean, again, based on what we, the simulation we did for this area, and that's what we find. But I think these are a broader discussion. So the second example I wanted to mention a little bit, again, Mark steal a little bit from this study also. And so this is a study by Zhang and Mark Pesson, and looked at some schematic modeling, use a schematic modeling approach, look at the basically middle continent US settings in terms of injection and induced seismicity pattern. And so there were two things I want to highlight here. One is that, so these are the vertical profiles of pore pressure that modeled, and the brown regions or yellow regions are the areas that potential failure. And then so these are the basement, and this is a basal aquifer. And so two things that I want to mention here. One already mentioned in the previous talk is that permeable faults in basement plays a significant role in facilitating pore pressure propagation, as showing if you look at these two sides, this without fault and this with fault, that fault clearly channels pore pressure diffusion into the normal fault here. And then this is another case where the fault is immediately under the injection well. And then this is a third case where the fault is a permeable thrust fault. So all these various scenarios all indicate that the fault is quite effective in terms of channeling. And then the other point I want to mention here is that the injection depth. And so what that study found that if you inject in the middle level instead of basal aquifer, middle level means that injecting the base in the aquifer, and then under the injection level, there is an effective impermeable or less permeable barrier that will practically prevent pore pressure propagate down. And so that's the second major point, I think, from this generic study. And again, I think it's very interesting, and these are further inquiry for more site-specific study. So, so this is a comparison between the middle level injection, basal injection, they both have fault. And so in this case, if you inject in the middle level, if there is a impermeable barrier at the bottom, and there won't be much pore pressure diffusion into the fault. And likewise here, there is a fault here, but the middle level injection because of the impermeable barrier there. And I think the difficult thing with this kind of scenario is that it's very difficult to have a continuous basal barrier. And you may have basal barrier somewhere, but I think a detailed characterization of that stratigraphy or permeability structure would be helpful. But I think from understanding the process perspective, this is a useful hint. So the third example that I want to quickly mention is the Greeley, northern Colorado. In May 31st this year, there was a 3.4 earthquake that just suddenly popped up. And so this is a map here in northern Colorado, and this is the local map, and this blue is the high injection well. Those are the disposal wells, and then these dots are the seismicity. And the bottom diagram shows the injection history of this well, and you can see there's a sudden increase. Now, in general, this area has seen its share of increased injection activity, and then in particular, there was, I think, 4 high injection wells in that area. And so it was quite interesting. As soon as the earthquake happened, the geophysicists and University of Colorado immediately started to install seismometers, and thanks for the NSF-supported IRIS facility. And so now the monitoring is still ongoing. And then hydrologists started to do some hydrogeological modeling. And so this is, okay. And so this is just a preliminary model, shows the, if you inject at this location, and these black dots shows the seismicity, and I think the location-wise it's pretty consistent. And then this is another scenario that we're still exploring, is looking at there is potentially there's a fault right under the injection point, and then so if that's the case, then the pore pressure again very easily goes into the basement to the basement. Okay, so to summarize, and I think the 2 points seems to merge from these pore pressure modeling studies. One is that high injection rate can be a major player in induced seismicity. And then the second is that fault could be quite effective in channeling pore pressure diffusion. So this in the case of Colorado and Middle Continent, and this in the case of Oklahoma and Colorado and Middle Continent. And so now the continuing challenge is that the background stress, I think I could probably skip that now because, again, Mark has mentioned and Austin mentioned quite a bit. And so the background stress, initial pore pressure, that we should have a really clear picture of what they are, and spatial distribution, and that's critical, and then identify faults, and I think Oklahoma is doing great in that direction. And And then the injection reservoir permeability structure, and I think I mentioned a little bit earlier, is it's important to know that some fine details in terms of the where we're injecting and which section of the injected interval actually is taking water, and some impermeable layers there may blocking or may not. And so just to put a final slide out here, is that I think even though I personally were preaching to say that pool pressure is critical to understand the spatial and temporal evolution of pool pressure from injection well to potential seismicity or just spatial evolution, temporal evolution. But I think it's more important that we take a system approach, process-based approach to the induced seismicity problem. And so there are three things here: the injection rate, and this is a maybe operational parameter, but this is an important hydrological stress that would be imposed on the system. And then if this is increasing this direction. And then the hydrologic diffusivity is one of the most important parameter that controls pressure dissipation and diffusion, and that's the geological and hydrological conditions that really go together. And if these two conditions are not good combination, then the risk of producing high pressure, and that make the system very prone to induce seismicity. And then on the base is really the geological background. I think we all agree and talked quite a bit today. And in terms of background stress, natural seismicity, and fault distribution, initial pressure, and that's, again, the geological, hydrological conditions of the system. And so again, I think we need to take a system approach and maybe develop models and hydrological models, hydromechanical models, and assess the situation. I think I'm going to stop here. I see red. Thank you.
Any questions for Chemin? Question there. Remember to repeat it.
Both in this talk and previous talk, there was a lot of talk about permeability of faults. And presumably, if the fault is permeable, then fluid flows into it and it's likely to have seismicity. In California, there's lots of faults that are in high geological environments that are impermeable. There's an offset of several hundred feet, and water table when you go across these faults. But still, these faults can have earthquakes. Like the San Andreas, South Dakota. So I'm not quite sure how much plays into the idea of permeable faults are safe and comfortable.
Yeah, so the question is that we emphasize here, if the faults are permeable, then the pool pressure goes into it and increase the risk of seismicity. But there are many less permeable or even impermeable faults. There are earthquakes as well. So I would say that I agree that fault, if it's a permeable that channels poor pressure into it, that increase the risk of induced seismicity. But if the permeability of the fault is not as permeable, that doesn't mean it. Well, the pool pressure can still be high, and the pressure gradient can still be high. It's just that the fluid will move pretty slowly in this kind of very low permeability fault. And in the long run, and that's not a guarantee that a low permeability fault would not induce seismicity. So I mean, even though we emphasize that permeable fault is risky, but I'm not saying less permeable fault is a safe bet. That's not the case.